Okay, so here's the thing that's crazy. We can react butadiene with ethene to form a ring between the two molecules. Madness. There's no nucleophile, there's no electrophile, everyone has COVID-19, and the world descends into chaos. This reaction requires simultaneous motions of electrons around a ring through a cyclic transition state. So we classify this type of reaction as a pericyclic reaction. We further classify this reaction as a cycloaddition because it is not only does it have a cyclic transition state, it also forms a ring product. So here's how it works. We talk about diene and dienophile instead of nucleophile and electrophile. The diene is exactly as it sounds, generally a 1,3 diene. The dienophile is anything with a reactive pi bond. Only the pi electrons react in this system, even though some will eventually form 2 new sigma bonds. Because 4 pi electrons participate from the diene and 2 participate from the dienophile, we call the reaction a 4+2 cyclic addition. Molecular orbitals can make a lot of sense of this reaction. The highest energy occupied molecular orbital, the HOMO, for the diene functions as the donor of electrons to the lowest energy unoccupied orbital, the LUMO, of the dienophile. Notice the symmetry overlaps. The shaded sections of the diene and the dienophile match up on both sides. This also helps us to understand which bonds are broken and which bonds are formed. Since the HOMO on the diene is losing its electrons to the LUMO through a sigma bond, it reduces the pi bond order in the diene to 1. Since the LUMO is gaining the pair of antibonding orbitals, it will reduce the pi bond order in the dienophile to 0, freeing up the other electrons to sigma bond back to the diene. This also explains why we don't see a similar reaction with a 2+2 addition. The 2+2 reactions do not have the right overlap between the HOMO and the LUMO, so it cannot occur. Interestingly though, different conditions will allow different reactions. The 4+2 addition reacts with a simple addition of heat. That's the Diels Alder reaction we just saw. But the 2+2 addition is not possible, just as we saw in the last slide. It's thermally forbidden. However, the 2+2 addition does occur in the presence of UV light. It's photochemically allowed. And here's why. When we use light, the electrons get elevated to the next energy level, so what once was the LUMO now becomes the HOMO and can react. It has the right symmetry to react with the LUMO of the other alkene. Cool. There are some limitations for this class of reactions. Since the reaction needs to have overlap between the HOMO and LUMO, they need to be close. This only happens in what is called the S-cis conformation for the diene. The single bond can rotate most freely, so the S-trans and cis-trans can usually interconvert fairly easily. But again, the reaction only occurs when the double bonds are pointed at the same side of the single bond, the S-cis conformation. This matters a lot more when the S-cis form is somehow prevented, either by conformational locking, with the locked bicyclic compound on top as an example, or when sterics prevent the S-cis form, like in this bottom molecule. The S-cis conformation can be locked in as opposed to locked out, with one of the most common examples being cyclopentadiene. Because one ring already exists, the Diels Alder reaction creates a bicyclic compound, with the reactive carbons of the diene becoming bridgehead carbons, connecting the original 5-membered ring to the new 2-carbon extension. You may have noticed way back on the very first slide that the yield for this reaction between butadiene and ethene is fairly low, around 18%. The truth is, we rarely actually use straight butadiene or straight ethene instead of swapping other substituents. Some of the types of things that we have talked about with aromatics, like the ideas of electron donating groups and electron withdrawing groups, can be really helpful to understand what dienes will be most reactive with which dienophiles. For the original reaction, notice that the HOMO of the diene is lower in energy than the LUMO of the dienophile. That means that we need to introduce a significant amount of energy to force the reaction to occur. But what if we could destabilize the HOMO and increase its energy? Anything that we can do to donate electron density into the HOMO will increase its energy and therefore its reactivity. So when we see methyl groups, which are electron donating by hyperconjugation, the diene is more reactive. If we have an ether, which is donating through resonance, the diene is even more reactive. Similarly, decreases in the LUMO energy will allow the dienophile more reactivity. Any conjugated pi bond to an electronegative atom will make the dienophile LUMO lower in energy and therefore much more reactive. So we see many examples with carbonyls conjugated with the dienophile. Another reason that the Diels Alder reactions are so powerful is that they generate products under stereo control. For example, the cis conformation of the dienophile is retained as a cis conformation in the ring. This makes sense since the reaction occurs during a concerted, that is to say, all at once, mechanism. There's no chance for the groups to rotate. Stereochemical retention works on both sides. If the double bonds of the diene are both trans or both cis, the addition of the dienophile will force them both into a cis conformation in the product. However, if the dienophile is trans, or the diene is a mixture of cis and trans, there are two possible products that can form, each enantiomers of the other. There's often no preference for one over the other, so the products are racemates, but still always trans. Diels Alder reactions offer even more control than that, though, even though orientation of an approaching dienophile is controlled. Since many dienophiles have conjugated pi systems that activate them, the dienophile generally approaches with this pi system oriented under the diene pi system. This allows for in-phase orbital overlap between the electron withdrawing group and the diene, which further accelerates the reaction. Because the group will orient one direction preferentially, in certain cases this indicates the formation of one product preferentially. The most common examples where this actually matters is where there is already a ring in the dienophile, like in cyclopentadiene. The dienophile will always approach opposite the bridging carbon for steric reasons, but it will also drastically prefer to approach with the carbonyl pointed in, which is shown in figure A on the left. When the new sigma bonds are formed, this locks the carbonyl substituent on the opposite side of the ring from the bridgehead. This would be the opposite if the carbonyl was pointed out. We'd end up seeing the carbonyl on the same side as the bridge. However, these exo products that are formed with the carbonyl pointing out are much less preferred and only appear as a minor product. Obviously, we can extend the rule even more if there are more substituents to favor the endo approach. In the case shown, each carbonyl prefers to stack under the diene orbitals, and the preference for the endo product, with the substituents opposite the bridgehead, is even more pronounced, with a 97% endo product and only 3% exo product. If control over stereochemistry through cis and trans forms of diene and dienophile and additional preference for endo products over exo products wasn't enough, we can also direct to particular regiochemistry through control over which orientation the diene and dienophile interact in. In the example shown, the reaction occurs most when the reactants are oriented as shown, with a much smaller portion of the products in the opposite direction. This makes sense if you draw all the resonance structures for the diene and the dienophile. Pause for a second and try to draw the resonance structures before advancing to the next slide. Notice that the resonance structures of the diene can localize extra electron density on the second carbon and on the fourth carbon of the diene. Of course, extra electron density on the second carbon doesn't do much good since it doesn't participate directly in the reaction mechanism. On the other hand, the electron density increase on the fourth carbon makes this carbon of the HOMO much more likely to be the donor to the LUMO of the dienophile. For the dienophile, we see a positive charge on the bottom carbon of the alkene as shown, which results in that carbon being a much more likely recipient of the electron density. The negative charge in the diene prefers to align with the positive charge in the dienophile, and they live happily ever after as the major product of a Diels Alder reaction. A chemical fairy tale. Diels Alder reactions always require heat to get enough energy to the HOMO to react with the LUMO. The products are also more stable in many cases under standard conditions, since the sigma bonds formed are lower entropy than the original pi bonds. We can see this in the delta H and delta G of the reaction shown. However, since the reaction is heated, it is not at standard conditions, and the more heat we add, the less standard it becomes. Any stability benefit we see in the delta G at standard conditions can be erased as temperatures are elevated higher and higher because the separate molecules deliver a much higher entropy, which matters a lot more at high temperature. This is exemplified by the formation of a dicyclopentadiene product at relatively low temperature, like the 150 degrees, or over time at room temperature. To regain the cyclopentadiene, the reactants are heated even hotter, allowing them to separate back into the cyclopentadiene.